March 30th, 1945. Rheinmetall Testing Facility, Düsseldorf. Oberingenieur Klaus Hartmann's hands trembled slightly as he adjusted the oscilloscope probe against the metal housing salvaged 3 weeks earlier from an overrun American anti-aircraft position near Remagen. "This should not be possible," he wrote in his classified technical assessment. No fire control system could achieve such tracking precision while simultaneously operating with such automation. Through the laboratory's grimy windows, he could observe the smoke rising from factories gutted by yet another Allied bombing raid. Tangible evidence of Germany's collapsing air defences. Yet here, mounted on his examination bench, lay physical proof that the technological disparity had grown even more catastrophic than the Luftwaffe's mounting losses suggested. The device before him, designated by American forces as SCR-584, represented a quantum leap in radar-directed anti-aircraft systems. The 6-foot parabolic dish antenna, the automatic tracking servo motors, the integrated analog computer that could calculate firing solutions faster than any human gun crew, each component demonstrated engineering sophistication that rendered German air defense technology obsolete by comparison. What neither Hartmann nor his colleagues yet fully grasped was that this single radar system explained a mystery that had been costing the Luftwaffe its most advanced weapons platform at catastrophic rates. The revolutionary Messerschmitt Me-262 jet fighters, Germany's technological trump card, were being destroyed with mechanical precision during their most vulnerable moments. Machines capable of 600 kilometers per hour were falling to ground fire with a success rate that defied every tactical calculation. The psychological transformation had begun months earlier, though few German commanders understood its true source. At jet airfields from Parchim to München-Riem, pilots had watched their comrades shot down during takeoff and landing with disturbing frequency. The jets themselves remained nearly untouchable once airborne and at speed, but the Jumo 004 turbojet engines required careful throttle management. Rapid movements caused flameouts. The narrow performance envelope meant every takeoff and landing became a period of acute vulnerability, and Allied anti-aircraft guns were waiting with preternatural accuracy. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The genesis of American radar superiority had occurred 5 years earlier, when British scientists shared their most revolutionary secret with their American counterparts. The TISAD mission of September 1940 brought to the United States a small copper device that would change the nature of warfare. The cavity magnetron, capable of generating powerful microwave frequencies at 10-centimeter wavelengths, made possible radar systems of unprecedented precision. By 1941, the MIT Radiation Laboratory had assembled a team of physicists and engineers with a single mandate: develop a radar-directed fire control system capable of tracking aircraft with sufficient accuracy to place anti-aircraft shells directly on target without requiring visual acquisition or manual tracking adjustments. The technical challenges were formidable. Existing American radar systems like the SCR-268 operated at longer wavelengths, providing rough range and bearing but lacking the precision needed for effective gun laying. Visual tracking methods worked in clear weather but failed completely at night or through cloud cover. German aircraft, and later the revolutionary jet fighters, exploited these limitations ruthlessly. Dr. Ivan Getting, working under the direction of the Radiation Laboratory's leadership, proposed a solution that seemed almost fantastical in its ambition. The radar would not merely detect aircraft, it would track them automatically, feeding continuous position data to an analog computer that would calculate the exact firing solution, accounting for target velocity, gun ballistics, and even atmospheric conditions. The key technological breakthrough was conical scanning. The radar beam, instead of remaining fixed, rotated continuously around the antenna's central axis. By comparing signal strength as the beam swept through its circular pattern, the system could determine not just where the target was, but precisely which direction to adjust the antenna to maintain perfect tracking. Motors mounted in the antenna base responded automatically to these calculations, keeping the radar locked onto the target without any human intervention. The system could operate at 4 frequencies, between 2700 and 2800 MHz, 10 to 11 centimeter wavelengths. It transmitted 300 kilowatt pulses at 1707 pulses per second. The mathematics were elegant, the physics unforgiving, the engineering brilliant. Initial tests at Fort Monroe in February 1942 demonstrated capabilities that exceeded even optimistic projections. The system could detect bomber-sized targets at 40 miles range. Once a target closed to within 18 miles, the automatic tracking mode locked on with 25-yard range accuracy and 0.06-degree angular precision, 1 mil of error. For practical purposes, if the radar could track an aircraft, the associated guns could hit it. Production contracts arrived within days of the successful demonstration. The Bell Telephone Laboratories developed the M-9 Director, an analog computer using 360 vacuum tubes and elaborate mechanical calculators to convert radar data into firing commands for 4 90mm M3 anti-aircraft guns. The complete system radar, computer, guns, power supply was mounted on trailers for mobile deployment. Chrysler Corporation's Dodge division received the massive production contract. By August 31, 1943, 610 systems had been manufactured. Final production reached over 2,000 units, including specialized variants for the Marine Corps and coastal defense installations. The first combat deployment occurred at Anzio in February 1944, where 2 SCR-584 units were rushed to the besieged beachhead to counter intense Luftwaffe attacks. German aircraft had been equipped with radar jammers designed to blind the older SCR-268 systems. The jammers proved completely ineffective against the centimetric wavelength radar. On the second night after deployment, 12 German bombers approached the beachhead. 7 were destroyed by radar-directed 90mm fire. A single reconnaissance aircraft appeared the following night to test the reconnaissance defenses. It was shot down within minutes. Luftwaffe air attacks on Anzio effectively ceased. 10 additional SCR-584 systems were emplaced within the week, creating an impenetrable defensive umbrella. The tactical revolution extended beyond simple air defense. The radar's precision allowed it to track artillery shells in flight, enabling American gunners to adjust their ballistic tables and locate German battery positions for counterfire. Vehicle detection capabilities extended to 26 kilometers in some terrain. The system could track ground support aircraft and guide them to targets with unprecedented accuracy, even in terrible weather. But the SCR-584's most devastating application came against Germany's V-1 flying bombs beginning in June 1944. The pilotless cruise missiles, traveling at over 500 kilometers per hour, were too fast for most fighters to intercept reliably. Visual tracking of the small, fast-moving targets proved nearly impossible for manual gun laying. The SCR-584, coupled with the newly developed proximity fuse that detonated shells when they passed near a target rather than requiring direct hits, transformed V-1 interception from desperate improvisation to mechanical slaughter. 20 SCR-584 installations were positioned along England's southern and eastern coasts, each controlling 4 90mm guns. By the end of August 1944, the combined radar and gun systems were destroying 70% of V-1s entering the coastal defense zone. On August 28th, the last day Germany launched V-1s before Allied ground forces overran the launch sites, 104 missiles were fired. The SCR-584 batteries destroyed 64. Fighters accounted for 14 more. Only 4 V-1s reached London. The rest crashed due to mechanical failures or fuel exhaustion. The success rate from 1 V-1 destroyed per 2,500 shells fired in early deployments to 1 destroyed per 100 shells. By late August, demonstrated the system's learning curve and the crew's growing proficiency. More critically, it demonstrated that speed alone provided no protection against radar-directed fire of sufficient precision. This lesson would prove devastating to Germany's jet fighter program. The Messerschmitt Me 262 Schwalbe represented German engineering at both its most brilliant and most tragically flawed. Development had begun in 1939, before the war started, as Project 1065. The design called for a revolutionary aircraft powered by twin turbojet engines, capable of speeds that would render it nearly immune to interception by conventional propeller-driven fighters. Technical challenges delayed the program repeatedly. The BMW 003 engines originally specified proved unreliable. Messerschmitt switched to Junkers Jumo 004 axial flow turbojets, which were heavier but more dependable. The engine weight distribution required sweeping the wings backward to maintain proper center of gravity, an aerodynamic feature that would later be recognized as essential for high-speed flight, though at the time it was implemented purely for balance. The first jet-powered flight occurred on July 18, 1942, but production remained stalled by material shortages, Allied bombing of manufacturing facilities, and most critically, high-level political interference. Adolf Hitler, convinced that Germany needed bombers rather than fighters, ordered the Me-262 developed as a ground attack aircraft capable of carrying bombs. Months were wasted modifying an airframe optimized for high-speed interception to carry ordnance. It was never designed to deploy effectively. By the time the first operational Me-262 units formed in late 1944, Germany's strategic situation had deteriorated catastrophically. Allied air forces operated with near-total impunity over the Reich. American heavy bombers flew in formations of over 1,000 aircraft, escorted by swarms of long-range fighters. British Mosquito bombers conducted precision night raids that German conventional night fighters struggled to intercept. The Me-262 offered a potential solution. With a maximum speed of 870 km per hour, over 200 km per hour faster than the best Allied fighters, it could slash through escort screens, attack bomber formations with devastating 30mm cannon fire, then accelerate away before enemy fighters could respond. In combat, properly flown Me-262s were almost untouchable, but they had to take off and land. The Jumo 004 engines that powered the Me-262 represented cutting-edge technology pushed beyond its operational limits by Germany's desperate circumstances. The turbojets operated at temperatures and stresses that required exotic metal alloys Germany lacked in sufficient quantities. Turbine blades were manufactured from mild steel rather than heat-resistant alloys, limiting engine life to 10 to 25 hours before replacement became necessary. More critically, the engines demanded careful throttle management. Rapid throttle movements caused fuel surging that led to compressor stalls or complete flameouts. Pilots had to advance power smoothly and progressively. During takeoff, full power could not be applied until the aircraft had rolled a considerable distance. During landing, power had to be reduced gradually while maintaining sufficient speed for control. These constraints created windows of profound vulnerability. During the takeoff roll, Me-262s accelerated slowly, remaining at low altitude and moderate speed for extended periods. During landing approach, they flew predictable patterns at reduced speeds while pilots carefully managed temperamental engines. In both phases, the jet's revolutionary speed provided no protection, and the SCR-584 radar tracked them perfectly. The first confirmed ground-to-air kill of a jet fighter occurred on November 26, 1944. A Me-262, a -2 Sturmvogel from the 3rd Gruppe of Kampfgeschwader 51, was approaching the RAF forward airfield at Helmond, near Eindhoven, presumably to conduct a reconnaissance of the facility. The aircraft was flying at moderate altitude and reduced speed standard procedure for reconnaissance passes. A Bofors 40mm gun of B.11. Detachment 2, 875 Squadron RAF Regiment, engaged the jet using radar direction from a nearby SCR-584 equivalent system. The gun crew tracked the target's approach, received continuous firing data from the radar-linked predictor, and opened fire at optimal range. The Me-262 was struck multiple times and crashed. All crew were killed. The kill was significant not because jet aircraft were inherently vulnerable to anti-aircraft fire. Any aircraft that could be tracked could potentially be hit, but because it demonstrated that radar-directed guns could track and engage targets flying at speeds and altitudes that defeated visual tracking. The jet's speed advantage, so decisive in air-to-air combat, provided no protection against electromagnetic detection and automated fire control. Over the following weeks and months, the pattern repeated with grim regularity. On December 17th and 18th, a total of 18 Me-262s attacked Helmond Airfield at intervals. The radar-directed Bofors guns of 2873 and 2875 squadrons damaged several jets, causing at least 2 to crash within a few miles. In February 1945, a B.6 gun detachment of 2809 Squadron RAF Regiment shot down another, Me-262 over Volkel Airfield. When Me-262s made their final appearance over Volkel later in 1945, another fell to the same unit's guns. The tactical reality became inescapable. Allied forces had deployed radar-directed anti-aircraft systems around every airfield that German jets might target. More critically, they had positioned mobile radar and gun units along the approach paths to known German jet bases. The Me-262s had to take off and land from specific airfields with prepared runways capable of handling their weight and speed. Allied intelligence identified these bases through reconnaissance and signals intelligence. SCR-584 units and other radar-directed gun systems were positioned to cover the approaches. German jet pilots found themselves flying through gauntlets of precisely aimed anti-aircraft fire during every takeoff and landing. The flak was not random or area suppressive. It was targeted, calculated, and devastatingly accurate. Lieutenant Klaus Hartmann, a veteran fighter pilot who transitioned to the Me-262 from conventional Messerschmitt Me-109s and Focke-Wulf FW-190s, described the experience in post-war interrogations conducted by American intelligence. The jets were magnificent once airborne and at operational speed, he testified. We could engage enemy bombers at our discretion, deliver our attack, and disengage before their escorts could effectively respond. The speed differential was simply too great for them to catch us if we maintained our energy. But taking off and landing became missions unto themselves. Allied anti-aircraft fire would begin tracking us the moment we became airborne. The shells would burst with uncanny accuracy, as if the enemy gunners could see us through clouds and darkness. We lost more aircraft and pilots to ground fire around our own airfields than we ever lost in air combat. The statistical evidence supported these observations with brutal clarity. Official records indicate that approximately 100 Me-262s were lost in air-to-air combat throughout the jet's operational service. However, total Me-262 losses exceeded 1,200 aircraft. The overwhelming majority, over 1,100 machines, were destroyed on the ground by bombing, caught during takeoff or landing by ground fire or prowling fighters, or lost to accidents that frequently resulted from the aircraft's demanding flight characteristics and engine reliability issues. The ratio was staggering. For every Me-262 shot down by an enemy fighter in air combat, 11 more were destroyed by other means. Ground-based threats accounted for a significant portion of these losses, with radar-directed anti-aircraft fire playing an increasingly prominent role as Allied systems proliferated. Oberingenieur Hartmann's examination of the captured SCR-584 in March 1945 revealed the technical foundations of this tactical catastrophe. The automatic tracking capability meant that gun crews did not need visual contact with their targets. The radar's 10-centimeter wavelength provided a tight beam that could distinguish individual aircraft from ground clutter and track them through weather conditions that made visual spotting impossible. The integrated fire control computer solved the ballistic equations continuously, accounting for target motion, projectile flight time, wind conditions, and the ballistic properties of 90mm shells. Human reaction time and calculation errors were eliminated from the fire control loop. The system tracked, calculated, and fired with machine precision. German air defense systems possessed nothing equivalent. The Würzburg radar, considered highly capable when introduced in 1941, operated at longer wavelengths and lacked automatic tracking features. German gun laying required visual tracking or manual radar operation by skilled operators. The fire control systems, while sophisticated, depended on human calculation and mechanical computers that were slower and less precise than the American analog systems. Against conventional aircraft flying at 300 to 400 kilometers per hour, these limitations remained manageable. Against jets flying at 800 plus kilometers per hour, they became crippling. German gun crews simply could not track and engage fast-moving targets with the precision required to achieve hit rates comparable to Allied radar-directed systems. The irony was profound. Germany had developed the world's first operational jet fighter, a technological achievement of extraordinary significance. The Me-262 was faster, better armed, and in many ways more advanced than any Allied fighter aircraft of 1945. In air-to-air combat, properly employed jets achieved kill ratios of 5-to-1 or better against conventional opponents. But that technological superiority meant nothing when the aircraft were most vulnerable during the 30 seconds of takeoff acceleration and the 60 seconds of landing approach, when engine limitations and flight characteristics forced them to fly slow, low, and predictable. And during those critical moments, Allied radar saw them perfectly. The spring of 1945 brought Germany's jet fighter program to its operational crescendo and its ultimate futility. By April, approximately 180 Me-262s were distributed among operational units. 143 served with 4-day fighter Gruppen, 21 equipped 2 fighter-bomber Gruppen, 9 operated with a night fighter Staffel, 7 flew reconnaissance missions with a tactical unit. On paper, this represented a formidable force. In practice, serviceability rates rarely exceeded 50%. Engine failures, fuel shortages, lack of spare parts, and the constant attrition from Allied bombing of airfields meant that commanders could never rely on having more than 70 to 90 aircraft actually capable of flight on any given day, and those aircraft still had to take off and land through radar-directed anti-aircraft fire. The largest single-day jet operation of the war occurred on April 10, 1945. 55. Me-262s took off to engage a massive American bomber formation, attacking targets in the Berlin area. It should have been a demonstration of the jet's potential impact on the air war. Instead, it became a demonstration of how technological superiority in one domain could not compensate for vulnerability in another. 27 of the 55 jets were lost by day's end. Most fell not to enemy fighters or bomber defensive fire, but to accidents during takeoff and landing, ground fire from radar-directed anti-aircraft systems, or attacks by Allied fighters that had learned to patrol over German jet airfields during the vulnerable moments when jets were slowest and most exposed. The mathematics were inescapable. A 50% loss rate was unsustainable under any circumstances. At that rate, the entire operational jet force would be destroyed within 2 sorties. No amount of tactical success against bombers could offset such catastrophic attrition of irreplaceable aircraft and pilots. General Lieutenant Adolf Galland, one of Germany's most experienced fighter commanders and highest-scoring aces, had been dismissed from his position as General of Fighters after disputes with Hermann Göring over jet fighter deployment. In February 1945, he was permitted to form an independent jet fighter unit, Jagdverband 44, and select its pilots. Galland chose the best. JV-44 became the highest concentration of fighter ace talent ever assembled in a single unit. The pilots' combined victory totals exceeded 1,000 enemy aircraft destroyed. These were men who understood aerial combat at the highest level, who had survived years of combat against increasingly overwhelming odds, who represented the absolute peak of Luftwaffe fighter capability. Even they could not overcome the fundamental problem. JV-44 began operations in April 1945 from München-Riem airfield, later relocating to facilities in Austria as the Allied advance continued. The unit flew Me-262-1 of fighters armed with 430mm cannons and, in some cases, R-4M air-to-air rockets, unguided projectiles that could be ripple-fired into bomber formations from standoff range. In combat, when they managed to engage enemy bombers, they were devastatingly effective. The combination of speed, firepower, and pilot skill allowed them to slash through escort screens, deliver attacks from angles and speeds that bomber gunners could not track, then disengage before the escorts could effectively respond. But Allied forces had learned. Fighter patrols orbited known jet bases continuously, waiting for takeoffs and landings. Radar-directed anti-aircraft positions covered the approaches. Medium bombers struck the airfields repeatedly, cratering runways and destroying aircraft on the ground. The jets were being strangled in their nests. Galland later reflected that JV-44 rarely flew more than half a dozen sorties per day and seldom shot down more than a couple of Allied aircraft per mission. The unit's potential impact was negated not by any deficiency in aircraft performance or pilot skill, but by the operational environment that made simply getting airborne and returning safely the mission's primary challenge. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The night fighter variant of the Me-262 represented another tragic manifestation of technological capability undermined by operational vulnerability. The Me-262B-1, a Solidus U-1 conversion, involved fitting the two-seat trainer variant with Fug-218 Neptune radar and Hirschgeweih antenna array's 8 dipole elements, projecting from the nose like stag's antlers. Only about 10 of these radar-equipped night fighters became operational by February 1945, serving with 10 Staffel Nachtjagdgeschwader 11 near Berlin. The small unit was tasked with defending the capital against RAF Mosquito bombers that conducted high-speed, high-altitude night raids beyond the reach of conventional German night fighters. In purely technical terms, the concept was sound. The Me-262's speed allowed it to catch the fast mosquitoes. The radar provided detection capability in darkness. The firepower could destroy bombers with short bursts. On paper, it should have worked. In practice, the unit flew approximately 70 sorties during its brief operational life and claimed 48 Allied aircraft destroyed, including 43 Mosquitoes. This represented an extraordinarily high success rate. Roughly two-thirds of all sorties resulted in confirmed kills. It demonstrated conclusively that when Me-262s could engage enemy aircraft under favorable conditions, they were nearly invincible, but the operational tempo remained minimal. 70 sorties across multiple months, from a unit with 10 aircraft, represented an average of less than 1 sortie per aircraft per week. This was not a function of pilot availability or mechanical reliability alone. It reflected the fundamental constraint that every mission required the aircraft to take off and land moments when they were exposed to the full weight of Allied air defenses. The night fighter operations typically employed wild sow tactics, wild boar, referring to single-engine fighters hunting bombers visually with the aid of searchlights and ground-controlled interception. The Me-262s would patrol over Berlin, guided by ground controllers who tracked incoming raids using radar and radio intercepts. When bombers were detected, the jets would be vectored toward them. Once airborne and at altitude, the jets were relatively safe. Allied night fighters like the Mosquito could not catch them. The speeds involved the Me-262, cruising at 600 km per hour or more, made interception by conventional aircraft nearly impossible. But every mission began with a takeoff through the radar-directed anti-aircraft defenses surrounding Berlin and ended with a landing approach through the same gauntlet. Oberleutnant Kurt Welter, who commanded the unit and became the top-scoring Me-262 night fighter pilot, later described the constant tension between tactical success and operational vulnerability. When we could engage the enemy on our terms, with altitude and speed advantage, the jet was unstoppable, he stated in post-war accounts. But we spent more time worrying about surviving our own takeoffs and landings than about enemy action. 27th, 1945. Herbert Altner, one of the unit's experienced pilots, suffered a double-engine flameout at altitude. Both Jumo 004 engines quit simultaneously, a catastrophic failure mode that left the Me-262 as a very poor glider with the aerodynamic efficiency of a brick. Altner and his radar operator, Reinhard Lomach, were forced to bail out. During the emergency egress, Lomach struck the aircraft's tail structure, either killing him instantly or rendering him unconscious. His parachute never deployed. He fell to his death while Altner, who had cleared the aircraft cleanly, survived. The incident underscored the Me-262's unforgiving nature. Engine failures that would be survivable in conventional aircraft often proved fatal in jets that lacked the glide performance needed for dead-stick landings. The broader strategic picture rendered individual unit successes increasingly irrelevant. By April 1945, Allied ground forces were advancing from both east and west. Soviet armies approached Berlin from the Oder River. American, British, and Canadian forces drove into central Germany. One by one, the jet fighter bases had to be abandoned as the front lines shifted. Aircraft were destroyed on the ground to prevent capture. Pilots retreated to bases further south, only to abandon those in turn as the collapse accelerated. Fuel supplies evaporated. Spare parts became unobtainable. The elaborate support infrastructure required to keep temperamental jet engines running simply ceased to exist. On May 8, 1945, Germany surrendered unconditionally. In the final hours before capitulation, some jet units continued flying. Oberleutnant Fritz Stahl of 2 Staffel, Jagdgeschwader 7, claimed the last Luftwaffe air victory of the war on May 8 around 4 p.m. Flying a Me-262 over the Ore Mountains, he attacked a formation of Soviet aircraft and shot down what he believed was a Yakovlev Yak-9. Soviet records indicate the aircraft was actually a P-39 Era Cobra. It was a pointless gesture. The war was over. The jet fighters, for all their technological sophistication and demonstrated combat effectiveness, had arrived too late and in too few numbers to alter the strategic outcome. More critically, they had been employed in an operational environment where their vulnerabilities were systematically exploited by an enemy possessing superior radar technology and the industrial capacity to deploy it in overwhelming numbers. The post-war interrogations and technical assessments revealed the full scope of the radar disparity. American investigators examining German air defense systems and captured Luftwaffe personnel documented repeated statements about the accuracy and effectiveness of Allied radar-directed anti-aircraft fire. German pilots described shells bursting with precision that suggested the gunners possessed some form of enhanced vision. They reported flak that tracked them through clouds, at night, in conditions where visual sighting should have been impossible. They noted that anti-aircraft fire became dramatically more accurate near certain Allied-controlled areas, particularly around captured airfields and major transportation routes. What they were describing was the systematic deployment of SCR-584 and similar radar systems across the theatre of operations. By early 1945, hundreds of these units were in service. They equipped anti-aircraft batteries defending every significant Allied installation. They covered the approaches to German airfields that Allied intelligence had identified as jet bases. They provided defense against V-1 flying bombs, conventional aircraft, and increasingly against Germany's jet fighters during their vulnerable moments. The technical examination Hartmann conducted in March 1945 confirmed what operational results had already demonstrated. The SCR-584 represented a generation of radar technology beyond anything Germany had fielded. The automatic tracking, the precision of the fire control solution, the integration with proximity-fuzzed ammunition that did not require direct hits, these capabilities combined to create an anti-aircraft system of unprecedented lethality. Germany possessed nothing equivalent and lacked the time, resources, and industrial capacity to develop and field comparable systems before the war ended. The Würzburg radar remained the standard for German air defense throughout the war. It was a capable system by 1941 standards, but had been overtaken by Allied developments. German fire control computers remained mechanically based, slower and less precise than the American analog systems using vacuum tubes. The mathematical reality was unforgiving. An anti-aircraft system that could engage targets without visual contact, track them automatically through any weather conditions, calculate firing solutions with mechanical precision, and achieve kill probabilities. Measured in single-digit percentages per shell fired, represented a tactical revolution, combined with proximity fuses that increased the effective lethal radius of each shell. Such systems transformed anti-aircraft warfare from area suppression to precision engagement. Against this technological backdrop, the Me-262's speed advantage became largely irrelevant during takeoff and landing. You cannot outrun electromagnetic radiation. You cannot maneuver away from radar tracking that updates positions hundreds of times per second. You cannot use clouds or darkness for concealment against centimetric wavelength radar that sees through weather with perfect clarity. The strategic consequences extended beyond the immediate tactical defeats. Germany had invested enormous resources in the Me-262 program. More than 1,400 aircraft were produced, representing hundreds of thousands of man-hours of skilled labor, vast quantities of strategic materials including exotic alloys and precision machining, and the diversion of engineering talent from other critical defense programs. Yet fewer than 300 Me-262s ever participated in combat operations. The remainder were destroyed on the ground by Allied bombing, abandoned as bases were overrun, or simply sat incomplete in factories as the supply chains collapsed. The operational jets, despite achieving impressive kill ratios in air-to-air combat, could not sustain the sortie rates necessary to affect the strategic air campaign. American heavy bombers continued flying over Germany in thousand-plane formations. British Mosquitoes continued their precision night raids. The combined bomber offensive continued grinding down German industry, transportation infrastructure, and fuel production. The jets, for all their technological brilliance, represented a tactical success within a strategic catastrophe. The human cost on the German side reflected the futility of fighting with inferior supporting technology, regardless of platform superiority. Me-262 pilots, many of them experienced veterans, transferred from conventional fighter units, died in crashes caused by engine failures, were shot down during vulnerable takeoff and landing phases, or perished when their airfields were bombed. The jet's accident rate remained shockingly high throughout their service life. The engine's unreliability, the aircraft's demanding flight characteristics, and the inadequate pilot training resulting from fuel shortages combined to create survival challenges even without enemy action. Those who survived the war bore witness to a technological revolution that had occurred too late and too incompletely to matter strategically. They had flown the future aircraft with performance that would not be matched by operational Allied jets until several years after the war. They had achieved individual victories against overwhelming odds, demonstrating skill and courage that transcended any evaluation of their cause's moral bankruptcy. But they had done so while blind to the electromagnetic dimension of warfare, where Allied superiority was absolute. German pilots flew without understanding that enemy radar tracked their every movement during the moments when they were most vulnerable. They attributed accurate flak to luck or exceptional skill by enemy gun crews, not recognizing that automatic tracking and analog computers eliminated both variables from the fire control equation. The examination of the SCR-584 in March 1945 came too late to inform any tactical or operational response. By that point, Germany had weeks remaining before total collapse. No countermeasure could be developed, produced, and fielded in the time available. The examination served only to document the technological disparity for historical record and to inform the bitter understanding among German engineers and officers that they had been fighting against enemies whose capabilities they had fundamentally misunderstood. The Allied technological advantage extended beyond radar into every domain that mattered for sustaining modern warfare: industrial production capacity, raw material availability, scientific research resources, engineering expertise, manufacturing quality control in every category, the Allies possessed advantages that Germany could not overcome through tactical brilliance or operational innovation. The Me-262 story exemplified this reality. Germany had achieved a genuine technological breakthrough in turbojet-powered fighters. The aircraft design was sound. The engines, despite reliability problems, represented pioneering work in a new propulsion technology. The pilots demonstrated extraordinary skill and determination, yet none of it mattered strategically because the supporting infrastructure, fuel supplies, spare parts, trained mechanics, operational air bases secure from enemy attack could not be sustained, and crucially, because Allied radar technology had evolved to the point where it could negate the jet's primary tactical advantage during the critical moments when that advantage was least applicable. Speed provided no protection against radar that could track targets perfectly regardless of weather or visibility. Surprise attack tactics meant nothing when radar detected approaching aircraft dozens of miles away. Maneuverability was irrelevant when automatic tracking systems followed every movement and calculated firing solutions faster than human reflexes could respond. The post-war assessment by American and British intelligence services documented these realities exhaustively. Captured German equipment was examined, surviving engineers and scientists were interrogated, operational records were analyzed. The conclusion was consistent across all sources. German air defenses had been comprehensively outmatched by Allied radar technology, particularly in the automatic tracking and fire control capabilities represented by systems like the SCR-584. This technological disparity extended to other domains as well. The British H-2S ground mapping radar allowed bombers to navigate and identify targets through any weather. The American AN/APQ-13 radar bombing system provided similar capabilities. German night fighters, while equipped with effective airborne intercept radar like the Liechtenstein SN-2 and later FUG-220 systems, operated in a reactive mode, attempting to counter Allied initiatives rather than dominating the electromagnetic spectrum. The strategic bombing campaign succeeded not merely because of numerical superiority in aircraft and crews, though those advantages were decisive, but because Allied technological capabilities, radar navigation, radar bombing, radar-directed fighter control, radar-directed, anti-aircraft fire created an operational environment where Axis defenders fought at comprehensive disadvantage. Individual German technological achievements, like the Me-262, or the Type XXI submarine, or the V-2 rocket, demonstrated impressive engineering capability, but none existed within a supporting technological ecosystem sufficient to employ them decisively. The jets lacked fuel and secure air bases. The submarines lacked time to reach operational numbers before the war ended. The rockets lacked guidance systems precise enough to hit military targets reliably. In contrast, Allied technological developments were embedded within industrial and logistical systems capable of producing and deploying them at scale. The SCR-584 was not a handful of experimental prototypes. It was a production weapon fielded in thousands, distributed throughout every theatre where it could contribute to operational success, supported by training programs that prepared crews to operate it effectively, and integrated into tactical doctrines that maximized its capabilities. This systematic approach to military technology development and deployment reflected the fundamental advantage possessed by nations with intact industrial bases, secure research facilities, abundant raw materials, and the time to refine systems through iterative testing and improvement. Germany, by 1944 to 1945, possessed none of these advantages. The Reich fought with the technological base it had developed before the war and in the early war years, when resources were less constrained. As Allied strategic bombing degraded German industry, disrupted transportation networks, and forced the dispersion of manufacturing to less efficient facilities, the technological gap widened. German systems became less reliable as quality control declined. Development programs stalled as resources were diverted to immediate operational needs. The most capable, scientists and engineers were scattered across multiple competing programs without adequate coordination. The result was technological achievements that could not be translated into operational success. The Me-262 exemplified this perfectly, a revolutionary aircraft that demonstrated genuine superiority in its design domain, rendered largely ineffective by the broader technological and operational environment in which it had to operate. The final accounting was brutal in its clarity. Approximately 1,433 Me-262s were built during the war. Combat losses to enemy action totaled several hundred aircraft, but the overwhelming majority of losses occurred on the ground or during the vulnerable phases of flight when the jet's speed provided no protection. The operational impact, while locally significant in some engagements, never approached the level necessary to alter the strategic air campaign's trajectory. The last Me-262s surrendered in early May 1945. Some were captured intact and shipped to the United States, Britain, and the Soviet Union for technical evaluation. These captured aircraft influenced the next generation of jet fighter designs in all three nations. The swept-wing configuration, while initially adopted by Messerschmitt for center of gravity reasons, proved essential for high-speed flight. The lessons learned from examining the Jumo 004 engines informed Allied turbojet development. But the operational lessons were equally important. The Me-262's vulnerability during takeoff and landing demonstrated that pure performance advantages in the air combat domain could be negated by technological superiority in supporting systems like radar and fire control. The jet age had arrived, but it required new tactical doctrines, new defensive systems, and new approaches to air operations that protected fast-moving aircraft during their vulnerable moments. The SCR-584 and similar Allied radar systems had demonstrated the decisive advantage that came from automatic tracking and precision fire control. Post-war air defense systems across all nations would incorporate these principles, evolving toward fully automated missile systems where human operators supervised rather than directly controlled the engagement process. The electromagnetic dimension of warfare, barely understood at the war's beginning, had become dominant by its end. Radar for detection, navigation, bombing, and fire control, radio for communication, command, and coordination, electronic countermeasures to jam enemy systems, signals intelligence to intercept and decode enemy communications. The side that mastered these invisible technologies held decisive advantages regardless of platforms' visible characteristics. Germany had understood portions of this reality. Luftwaffe night fighters used radar effectively. German submarines attempted to develop radar warning receivers, but the Becker systematic integration of radar throughout all aspects of military operations. The Allied approach, exemplified by systems like the SCR-584, created a technological advantage that tactical innovation could not overcome. When Oberingenieur Hartmann completed his examination of the captured American radar in March 1945, he understood that he was documenting a defeat that had already occurred. The system before him explained why Germany's most advanced weapons had failed to achieve strategic impact. It revealed the technological disparity that no amount of courage or skill could bridge. His report, classified and filed in archives that would be captured within weeks, concluded with a bitter assessment. The Allies have achieved comprehensive superiority in automatic radar tracking and fire control. This advantage, combined with their industrial capacity to deploy such systems in quantity, has rendered our air operations increasingly untenable. 6.2. Despite its exceptional performance characteristics, cannot overcome the vulnerability imposed during takeoff and landing, when enemy radar-directed anti-aircraft fire can track and engage with precision that renders altitude, speed, and maneuverability irrelevant. It was an epitaph for Germany's jet fighter program and a recognition of how technological warfare had evolved beyond the visible domain of aircraft performance into the invisible realm of electromagnetic radiation and automated fire and control. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.